Okay, I was told to start at 5 past. So let's go ahead and get started. So we had slightly informally given the general definition of what's called a local spectral expander, a spectral high-dimensional expander. What I didn't make sort of fully formal was this final conditioning part that was hopefully clear over in the bipartite or the partite case that used to be over there. But let's be careful about what these conditionings are over here. So just as a reminder, we said that the natural analog of this sort of pairwise independence definition that we had in the ordered case was just picking a random pair from x1 through xd, which was the same thing in this diagram as starting with a random d hyperedge and then subsampling a random edge, giving us sort of this underlying graph of the complex. And the first thing that we were requiring is that this underlying graph of the complex is a lambda expander. This sort of captures pairwise correlations in the complex. And then we said we also want this to hold under conditioning after I fix some subset of the variables. So let me now formally say what that means. Really what I want to do is sort of condition on some vertex, say 1, lying in x1 through xd. And how would I do this over in this diagram? I would look at everything that contains the vertex 1, which I guess this part of the top is cut off, sorry. So I'm going to look in this diagram at all of the faces that contain 1. So here it's 1, edges 1, 2, 1, 3, and 1, 4, and triangles 1, 2, 3, 1, 2, 4, and 1, 3, 4. And then I'm basically going to look at just this, the conditional distribution over these faces containing 1. And then I want to look only at the remaining unset variables, right? So in some sense, I've set one of these variables to be 1. I only want to look at the remaining values, so I'll then remove 1 from this structure. So I'll get a 1 lower dimensional distribution by removing 1. So I'll get empty set. The edges will become, the edge 1, 2 becomes vertex 2, 1, 3 becomes vertex 3, 1, 4 becomes vertex 4, and the triangles become edges, right? 1, 2, 3 becomes 2, 3, et cetera, et cetera. So I get a 1 lower dimensional distribution or subsimplicial complex, which distributionally is just the conditional distribution of this hypergraph, conditioned on containing 1. And I could do this procedure with any face in the hypergraph, right? I just select everything that contains it, and then I remove it to get the conditional distribution. So let me write it down formally as a combinatorial object as well. Combinatorially, we can view these as local neighborhoods, right? What I'm doing here is selecting the neighborhood of 1. So these are usually called the links of X. So for a given T in the simplicial complex X of any particular size, so I'm not fixing the size, the link XT is sort of the local subcomplex that is the neighborhood of T. So it's a D minus T dimensional subsimplicial complex. And it's just defined combinatorially exactly like I said. I look at all of the faces in the complex that contain T, and then I remove T from them, right? So, S without T such that T is in S and is in X. It's like the, exact set formalism. But just think of it as I take everything containing T and I remove T. There's nothing more complicated than that. And there's also, of course, a natural induced distribution, right? This is a weighted complex, and it's just the conditional distribution upon containing T, right? So I have my top level distribution pi3 in this diagram, and I would just restrict pi3 to all these guys that contain 1, right? So formally, the distribution would be the weight of, sorry, did I do this wrong? The weight of S, yeah. Sorry, give me a second. That should be S prime. Sorry. So formally, the weight of S in the link of T is just the top level weight of the face S union T, right? The original guy that we had before we removed T, normalized by the total weight of everything containing T. Okay, it's just a conditional distribution on containing T. That's the definition of the link. And we already discussed, once I have this sort of high-dimensional link, how I get an underlying graph, right? I pick a random pair from this distribution, and this gives me the 1 skeleton, or maybe I should call it a 2 skeleton. It gets me some underlying graph, And now I can define full high-dimensional expansion, which says that the graph underlying every link of X, including when T is the empty set, this is just the complex X itself. So the graph underlying every link, all of these pairwise conditional marginals should be lambda expanders. That's the full definition. So we'll rewrite this as maybe for all links of codimension at least 2. What do I mean by codimension at least 2? If I fix something in the top level or one level below, I'm left with a 0 or 1-dimensional object, right? There are no edges, so it doesn't make sense to talk about expansion of this object. As soon as I go at least 2 levels down, I have a non-degenerate simplicial complex, and I can talk about its expansion. So for every link that is non-degenerate, that's a codimension at least 2, the underlying graph, let's say link xt, the underlying graph of xt is a lambda expanded. Okay. Any questions on links or the local spectral definition of high-dimensional expanders? This is called local spectral expansion. I guess maybe I should say that a one-sided local spectral expander is when you have a one-sided expander on the links. A two-sided local spectral expander is when you have two-sided expansion on the links. Yeah, it's just x2, x1, x0 of the complex. And it's a weighted graph, right? The weights pi2 are given by take a uniform pair of a random hyperedge. And so this captures, I really like, I want to emphasize this captures pairwise correlations in the complex. Because what's the probability that I draw an edge VW? It's exactly corresponding to how often V and W occur together in a hyperedge in the complex. So this really captures pairwise correlations, and spectral expansion, following our intuition from the apartheid case, is really saying that all the pairwise correlations in this complex are bounded. The things sort of look independent. Yeah. So when you say any two layers between these graphs, you mean if I look at the inclusion graph, which is like the literal graph I've drawn here? So we will prove in the last lecture that this is like the big theorem. This is how the Mihailov-Vazirani conjecture was resolved. It turns out that this definition implies that the random walk between levels of these, which is exactly the bipartite graph, is nearly as good as an expander as it can possibly be. Yeah, the current definition is that each of these local graphs expands, right? That doesn't necessarily say anything about the graph between 3 and 2. The underlying graph of the simplicial complex expands. That's the definition. Yeah. Right, good. So this link, the graph, the corresponding graph is just K3, right? I have 3 vertices, 2, 3, 4, and all of the edges between them. So this is indeed a high-dimensional expander, right? Yeah, we have not talked about expansion between the inclusion graph. We will prove, hopefully, by the 4th lecture, that this definition, in fact, implies that the inclusion graphs expand, have sampling, have all of these nice properties, but it's not at all a priori obvious that that this is true. We'll get there, but yeah, it's just the underlying graphs expand. Yeah. Maybe we should talk offline. Yeah, let's talk after about it. Okay, I want to do a couple examples, and then I actually want to prove sort of the first main theorem about HDX called the trickling down theorem. So let's do some basic examples. So one of them was actually already written there. So okay, maybe I'll start over here. So this is the complete complex on four vertices. The first example that we'll look at, in the unordered case, we can of course really think of high-dimensional expanders as sort of being a sparse model for the complete hypergraph, right? For every possible hyperedge being present. So maybe we should at least check that the complete hypergraph is indeed a good high-dimensional expander in this definition. So example one. Complete D-uniform hypergraph or simplicial complex. Okay, so my claim is that this is a one-sided zero local spectral expander and a two-sided what is it, like 1 over n minus d plus 1 local spectral expander. So think of the number of vertices n as being much, much, much larger than the dimension d, like fixed d as a constant and n goes to infinity. So these are extremely good expanders, right? 0 is the best you can possibly have, essentially, which makes sense because this is the object we're trying to copy. And 1 over n is essentially 0, right? This is basically going to 0. Does anyone want to tell me the proof of this? So what are the what's the underlying graph of the complete complex? Just looking at this diagram. Yeah, it's just a complete graph. Right, so all of the local links are uniformly weighted complete graphs. Right, so okay, I won't actually go through the calculations, but the link graphs are complete. And in particular, the top links, right, when I fix D minus 2 guys and I look at their skeleton, that's a complete graph on n minus d plus 2 vertices. So this is coming from, that's sort of the worst case. This is coming from the worst case expansion of the complete graph on n minus d plus 2 vertices. So links are complete. That'll be the full proof we give of this. Okay, so that's example one. Second example is actually sort of where we started before. I want to look at the complete partite complex, also equivalent to product spaces, independent random variables, right? The whole spiel was that in the partite case, we're supposed to be generalizing independence and complete partite graph. So it better be a good high-dimensional expander. So complete d-partite. Is this too high? No, it's below the line. D-partite complex. So let me just draw this. So this is where we have every possible edge between or hyperedge across all the four parts. Okay, so here the links are partite, right? If I fix everything but say 1 and 2, I get a complete bipartite graph. So this will not be a good two-sided high-dimensional expander, right? This has an eigenvalue of -1. So the max of lambda 2 and lambda n is quite large. But on the other hand, it should be a very, very good one-sided or partite one-sided high-dimensional expander because the eigenvalues of complete multipartite graphs are 1 and negative. So this turns out to still be a one-sided zero local spectral expander. And yeah, I guess it's an exercise to prove that. So all the links, I just said the top links are bipartite, but it's easy to check that all of the links of this are just complete multipartite graphs, right? If I fix any subset of this, I'm just going to get the complete multipartite graph on the remaining parts of this object. So it's an exercise to show that those have lambda 2 less than or equal to 0. Actually, one more, I want to spend a little bit more time on this example. The first thing that I want to say is, okay, I already said that this is sort of equivalent to looking at independent random variables. I just want to highlight that, for instance, if I just have 2 vertices on each part, that this is an object that hopefully all of you are familiar, very, very familiar with the properties of. So this is, I have like coordinates, 1, 2, 3, 4, up to D, and the hyperedges are, I pick, 0 or 1 on every possible coordinate. This is exactly the hypercube, right? This is exactly sort of the simplicial complex version of 0, 1 to the D. More generally, if I, had n guys in each component, this would exactly be a representation of sort of the product space n to the D. And so this is saying, these products are perfect high-dimensional expanders, are perfect zero local spectral expanders. And like I said toward the beginning, we're going to see this theme of all of these results we know about product spaces, like FOIA analysis, like fast mixing of random walks. We're going to show how to generalize all of these, the tools used in these domains, over to general high-dimensional expanders, not just these. Even generalizing to zero local spectral is already pretty impressive, as the next example we're going to see. But we'll even generalize the sort of general high-dimensional expanders. Right. The other thing I wanted to say is to contrast the two definitions of high-dimensional expansion I gave you. Right. One of the definitions, I gave you a partite definition that looked at each pairwise marginal. So looking at this, that's like looking at the expansion of each, individual bipartite component of this graph. Local spectral expansion looks at the spectral expansion of all of the components together. That's the only difference between these two definitions. One of them looks at all the parts at once and looks at the spectrum of that matrix. One of them separately looks at all of the bipartite components between them. In the exercises, hopefully, you'll show that up to a factor in 1 over dimension, if I require these in all links, the definitions are exactly the same. Doesn't really matter if I look at the spectrum of the full graph or I just look at the spectrum of each bipartite component. They're the same up to a factor in dimension. Okay. So let's see, these are sort of trivial examples of high-dimensional expanders, right? In the sense that these are actually the objects that we're trying to model, that we're trying to sparsify. So I'm not going to give you a sparse example yet, but I am going to show you a non-trivial example of something that, at least the first time I saw, I was pretty surprised that it was a high-dimensional expander. And in fact, lots of these arise from looking at certain combinatorial objects on graphs. The most famous one is spanning trees. It turns out that the set of spanning trees, viewed as a simplicial complex in a way that I'll write, is a nearly perfect high-dimensional expander. So example 3 is a spanning tree complex. So what is this? This is given a graph G. I'm going to define a slightly weird simplicial complex where the vertices of the simplicial complex are going to be the edges of G. So x0, the vertices, is the edges of G. And the top level, let's say this is on, let's say this is on n vertices. This will actually be an n-dimensional, n-1 dimensional complex. The top level of faces are just going to be all collections in G that form a spanning tree, right? So if I draw a graph, this is E1 through En-1, such that this is a spanning tree of the graph. Right, so maybe I have, I don't know, I take I guess I need to add some more edges, but so any sub-collection of these edges that forms a spanning tree will be in Xn-1, and then I'll generate. Thank you. The mathematician came out. X1. The vertices are edges. Thank you. And the top level faces are these collections that form a spanning tree. And it turns out, somewhat surprisingly, that this is also a zero local spectral expander. So in particular, I'm not going to go through this. It's a nice exercise. If you look at the links, soon we're about to prove that you'll only have to look at codimension 2 links, which makes things a little bit easier. But these give you complete par-type graphs, and therefore you'll get a 0 local spectral expander. So these are, of course, still very, very dense objects, right? There are a huge number. For every vertex, it lies in a huge number of spanning trees. So this isn't like getting us a sparse construction of HDX, but it's some pretty interesting non-trivial structure that has this notion of approximate independence. And we'll see later that using this fact, we'll see how to approximately sample a spanning tree out of exponentially possible trees, possibly many trees in polynomial time. So we'll get very non-trivial facts about these objects from using this local spectral expansion. I mean, they're just defined by downward closure. So xi is defined by taking a random spanning tree and then taking a random subset of I of the edges. Sorry? It's not, no, in example 1, you have all possible n-1 sets. So this would be like, I don't know, maybe there are lots of cycles and edges in here, right? The complete hypergraph would be I take all possible sets of edges. Right? They might form cycles. They might not be a spanning tree in this graph. Yeah, good. So I guess xi is exactly forests of I edges. Although the distribution may be weird, right? It may not be a uniform distribution. It's some distribution over size I forests. Thank you. Yes. Actually, from now on, basically, the top level distribution will always be uniform, and pi I will be given by downward closure. You don't have to do this. It just usually it's the typical thing to look at. Actually, in sampling, often they look at things coming from a Gibbs distribution or something, so it's not uniform. But in our case, we'll just stick with uniform distribution. Yes, thank you. That's an important clarification. This is not true if it's not a uniform distribution over the top. Good. Okay. Let's move on. So we saw in applications to codes, and I'm sure you can imagine in applications to complexity and towards PCPs, we don't really want things of this density. We want sparse or what are called bounded degree constructions of high dimensional expanders, right? In the graph case, we wanted to build these graphs that had as low degree as possible, right? Every vertex was only connected to 5 other guys, and yet it had this sort of incredible approximate independence property that despite this incredible correlation, where if I fix the first guy, there's only 5 out of n possible options, all these correlations sort of cancel out, and it still acts like it's independent on average. So the big question then is, can we actually construct even 3-dimensional versions of high-dimensional expanders that are bounded degree, where every vertex sits only in 10 triangles or something like this, and yet in every link, you're a spectral expander. Okay, so what's the first thing we might want to try? Let's sort of recall the ways that Madhur talked about being able to build an expander. The first one, I think, that he mentioned was just taking a random graph, right? We didn't prove this, but a random sparse graph, even I think degree 3, if done with matchings, will be a very good expander. So question, are random sparse hypergraphs HDX? I don't know, take a poll of the audience. Do people think that these will get us high dimensional expansion? Say I take a random linear number of hyperedges. I have n vertices and I pick a random 100 times n hyperedges. Let's say even more. Let's say I have a k-dimensional. I'm looking at n choose k, and I pick every hyperedge with probability, pick hyperedges with probability roughly like, I don't know, 1 over n independently. So this will have, about n to the k minus 1 total hyperedges, right? There are n choose k, about n to the k total possible guys. I pick every one independently with probability 1 over n. This is still a really dense object, right? There are n vertices, and n to the k minus 1 polynomial blow up in k phases. So this is still a really dense complex. Do people think this will be a high dimensional expander? Yes. No, it will not be. Why? Because the links will be disconnected. So, unless maybe should I pick 10 to the k minus 2? Did I? Wait. No, an n to the k minus 1. I'm picking in a top link. I'm picking every edge. Aren't I picking every edge with probability 1 over n? Oh, maybe, okay, maybe I screwed it up. Okay, maybe it should be n to the k minus 2. No, but a sparse graph is not an expander. If I pick things with 1 over n randomly, I'm not picking a random deregular graph. I'm picking each thing independently of probability. So no, okay. Aha. Okay, I've cheated slightly because I didn't pick a random deregular matching. I picked each thing independently. The point is that there's a connectivity threshold at log n over n. Right? If I look at a, so now like look at a codimension 2 link of this object. Right? So fix some 1 through k minus 2, and look at all of the hyperedges now, the random hyperedges that'll contain 1 through k minus 2. This is the graph. We need this to be an expander. But each guy is going to appear with probability about 1 over, 1 over n, or maybe it should have been 10 over n or something like this. And I'm not going to go through it, but it turns out that a random graph of this sort is known to be disconnected with very high probability until I take each edge with probability like log n over n. So it turns out that even these extremely dense complexes are not high-dimensional expanders. Yeah, sorry, was there? Okay. Are not high-dimensional expanders. Yeah. Sorry. So, yeah, pick a 10 over n fraction, 100 over n. And now I'm fixing a link and I'm saying, look at this local, like look at the random graph on this link that's generated from this process. It's just going to be an Erdos-Renyi random graph with probability 10 over n. But sharp threshold theorem says, until you hit log n over n, the graph's disconnected with extremely high probability. So in fact, like almost every link is going to be disconnected in this complex. So it's a terrible high-dimensional expander. On the other hand, if you just looked at the one skeleton, it's going to be complete, right? So it's definitely going to satisfy all these. Like if I don't require conditioning, if I just want this like high-dimensional expander mixing lemma, or all pairwise marginals are good, it'll certainly satisfy that. But it's going to fail this conditioning notion that after fixing k minus 2 guys, I still need to be an expander. Random things will not work for this. Morally, what's the reason? Because if I'm trying to build a sparse complex that's locally expanding, morally, I want things to be globally sparse, but somehow locally dense. Right? The denser I am, the easier it is for me to be expanding. So indeed, when you see constructions, somehow they'll come from this magical structure that you get local objects around each vertex that are extremely dense, but somehow you fold things in some algebraic way so that the global object remains sparse. And this is inherently something that requires structure. If I pick a random object with high probability, things are going to be really evenly spread out. So you're not going to see local things being much denser than the global average, which is what you need in a high-dimensional expander. So this is why, at least naively, random constructions do not work for HDX. And modulo maybe achieving really weak, like half minus delta expansion, we don't know any random model that generates a good high-dimensional expander. Yeah. If I say I'm going to have a complete k minus 2 skeleton and then sorry, okay, maybe at n to the k minus 2 we don't know. Okay, yeah. Right, if you pick a matching, I guess, more carefully. But as soon as you go slightly sparser than this, which is still an extremely, we want there to be like O of n hyperedges, right? We want every vertex to sit in only some constant number of hyperedges. So yeah, as soon as you go to n to the k minus 2 or something like this, I think we don't know any random models that give you good constructions. Okay, yeah, good clarification. Okay, so the final thing that I want to state is sort of a magical, well, it's no longer magical due to some subset of people in this room, and Tali and Azar. but is the fact that bounded degree high-dimensional expanders actually do exist, that there are algebraic ways to construct these objects. So this was, I think, independently proved by several groups 10 years before this definition was actually given. People were studying generalizations of Ramanujan complexes, Ramanujan graphs to high dimensions. So this is independently, I have it written somewhere, Cartwright, Sol, and Juk, Lee, I always forget the exact name of the third guy, Sarveniazi. I think this is like 03, 04, 04. And then Lubatsky, Samuels, and Vishne, 05, all constructed some version of Ramanujan hypergraphs, which in particular says, you know, for any lambda greater than 0 and any k, there exists an infinite family of high-dimensional expanders of lambda local spectral HDX, where you know, the degree of each vertex, the degree is just the number of hyperedges that it sits in, or the degree of xn is at most lambda to the minus, let's say, theta of k squared. So did I do d and k? Let's do. Sorry, so this should be a d-dimensional HDX that has degree lambda to the minus d squared. So in particular, thinking of d as constant, like triangles or something like this, we indeed get constructions of expanders that have you know, arbitrarily good expansion and constant degree. I'm not going to go through these initial constructions are extremely involved. There's a beautiful construction of Kaufman and Oppenheim that came later, maybe 2018, that sort of gave an elementary construction of HDX. It's still some group theory. It's coming from some nice matrix groups. It's not some crazy quotient of a high-dimensional object, which the initial ones were. It's very beautiful. There's a super accessible exposition due to Prahladh and Ramprasad in 2019, some year. So if you want to know more about algebraic constructions of high-dimensional expanders, I strongly suggest reading this survey. It's extremely nice. Okay, but I actually want to go on to proving our first sort of main theorem about high-dimensional expanders. Yeah.
Here are all Ramanujan expansions. They are called Ramanujan complexes because the constructions are similar to the.
They're called Ramanujan because the spectrum of the Heck operators matches the spectrum in the affine buildings. So they are Ramanujan in this sense. However, that is a different sense than the links are not, these graphs are not Ramanujan. There is a different sense in that Ramanujan means that you match the spectrum of the infinite object that you come from, that I don't want to get into. That these are indeed, these ones are Ramanujan complexes. Here there's no object, so it's not even defined. Yeah, that's a whole other can of worms, like what Ramanujan means in these constructions that I don't want to touch. Okay, so let's actually prove some theorems about high-dimensional expanders. So hopefully you're somewhat convinced that these are natural objects, right? They're hypergraphs where all the variables act independent, and we can actually construct boundary examples. But why should you care? Why are these powerful objects? What can we do with them? What's the style of analysis that is done? So basically, the bread and butter of high-dimensional expansion is what people call the local to global method, which we sort of saw an example from earlier in Dinur in this AEL sampler type construction. And in some sense, HDX are going to give you this type of behavior on steroids. Because everything works conditionally, you get sort of local to global everywhere in your object, and it becomes a very, very powerful tool. So we're going to see today, hopefully I'll get through one example of that, and then the next two lectures we'll do example that resolved this big conjecture and mixing of random walks also through local to global theory. Okay, so one thing that you can notice about this definition of local spectral expansion is that it is in some sense both local and global. What do I mean by this? If I take X and I look at the underlying graph of X, this captures the global pairwise correlations of X. On the other hand, if I look at the links, it's capturing the local pairwise correlations in X. So the first local to global theorem that I'm going to prove to you is that in fact, it's enough to have local bounds on the correlations. That if I have only a promise of spectral expansion in the links, it turns out this actually implies global spectral expansion of the full one skeleton. This is sort of the first local to global theorem. It turns out you only need to have spectral expansion in the top codimension 2 links, and I immediately get it for free everywhere else in the complex. This is called the trickling down theorem. The rest of the complex has to be connected, but other than that, you'll get it for free. So this is, do it over here, the trickling down theorem of Zara Oppenheim. And I'm just going to do the 3-dimensional version here, and as an exercise, there's an easy induction that gets you a d-dimensional version. So given a three-dimensional complex X such that all one links, so all the links of vertices in this complex are lambda expanders. I'm just going to do one-sided. Assume I mean one-sided when I write lambda expanders for a moment. And 2, the underlying graph of X is connected. Then this actually implies that lambda 2 of this, let's write A is the adjacency matrix of the underlying graph of X, weighted adjacency matrix. Then lambda 2 of A is less than or equal to lambda over 1 minus lambda. In other words, just from having local spectral information about all of these local neighborhoods of the vertices and having connectivity of this underlying skeleton, I am going to infer, if lambda is small, that this skeleton is in fact an extremely good expander. And so as long as lambda is significantly less than 1/2, this is going to give me good expansion for the underlying one skeleton. And I'll mention there's a d-dimensional version of this theorem that's basically a corollary, because I just apply this inductively in the links, and then maybe there's a trick where you look at the skeleton. I'm going to leave this as an exercise as well. But so as a corollary, you get the same setup, but now d-dimensional complex X, such that the codimension 2 links have our lambda expanders, and X is connected, by which I mean all links of X. The underlying graphs of all links are connected. This implies the one skeleton underlying graph, is a lambda over 1 minus d minus 2 times lambda expander. So if d is 3, lambda over 1 minus lambda, this generalizes to high dimensions. So in fact, we don't have to look at all the links of as long as lambda is reasonably small, like 1 over d or 1 over poly d, we don't have to look at all the links. You only have to understand these top pairwise correlations in the complex. That will imply high dimensional expansion of the entire complex. Okay. Okay, so my hope is to actually prove this, or at least sketch the proof. Probably don't have much time, do I? Okay, well, let's give it a try. Any questions on the theorem statement while I erase the board here? Yeah. It's just the graph underlying the complex. Yeah. So I mean, the one skeleton is defined as I pick a random, sample a random D set from the top level, and then pick a random edge from here. Right? Pick a random VI VJ uniformly at random. This generates an edge, right, in some graph. That's the underlying graph. Okay. Yeah. So we're going to prove that this graph expands, given that the top links expand. Okay, so hopefully people recall from last time this characterization of lambda 2 by the Rayleigh quotient. So in particular, our goal let's see. Our goal is going to be to show that actually we'll just fix f to be the eigenvector corresponding to lambda 2 of the graph A that we want to analyze. To be a unit normalized eigenvector of lambda 2A, right? And otherwise, f is the vector such that AF is equal to lambda 2F. And we're trying to bound lambda 2 here, right? Where A is the graph of this one skeleton of the complex X. And we can do this by bounding this quotient that Medor talked about. It's enough to prove that the inner product of F applied with AF is less than or equal to lambda over 1 minus lambda. Right? Technically, I would write FF here, but I'm assuming F is unit norm. So this is just 1. Right? Okay, so my goal is to analyze this global inner product, where I'll remind people that this is this inner product over the pi2 distribution, right? The weighted distribution over the underlying graph of the complex. Yeah. So F is the eigenvector of lambda 2, so it's automatically orthogonal to, right? I guess I'm not actually using the definition of the Rayleigh quotient here, right? This is I'm just taking the vector F for a vector F in the second eigenspace, and I want to upper bound. This will be equal to F lambda 2 F, which is equal to lambda 2. So I'm just trying to upper bound this value. But we're going to do it through analyzing this inner product. Okay. So what information do I have? Right? I don't know any global information about this graph A or the one skeleton, the underlying graph of my complex, except that it's connected. But I do have local information, right? I know that on all of these links, on all of the restrictions to vertices, that my underlying graphs are spectral expanders. So I want to come up with some method where I'm going to divide this inner product up into an expectation over local inner products on the links. Right? I'm going to try to divide this into some sort of expectation over the links of some restriction of F. The inner product of F with the link one skeleton, which I know is a lambda expander. Okay, and then I'll just try to analyze this using the local expansion and pull it back to a bound on this global object. Right? That's sort of the general strategy. These local guys are graphs, right? Because I'm in 3 dimensions. So when I look at a link, I just get a graph. So I'm trying to do sort of this local to global propagation, where I just take an expectation of my global object, divide it up over, these are basically the 2-dimensional marginals of my distribution. I bound it locally by expansion, and I pull it back to a global bound. That's basically going to be the structure of the whole proof. Okay, so how do I actually do this? So this is going to follow through, I need some sort of lemma, right, that relates FAF to some expectation of the local functions. So let me be a little bit more formal about this. This is often called Garland's method or Garland's lemma. After Garland, who did something similar in a paper in '73 analyzing cohomology, But so this method is sort of attributed to him, but it's been used a lot more in the context of spectral expansion recently. So to define this, I haven't told you what this function fv is. So I need to define some sort of localization of my global function f to the link graphs. Right? So the first thing I want to define is the restriction thank you. So f is a function on the edges of x, right? We're analyzing the, oh, I'm sorry. It's on the vertices of x. Yeah, thank you. Actually, so that was wrong. This should be over pi 1. Yeah, I erased it and wrote pi 1 because it's wrong. Thank you. Thank you. Good catch. Yeah, sorry. This is supposed to be a function over the vertices. We're just analyzing the spectral expansion of this graph. Sorry about that. This should be over pi 1. Yeah, and this is a function f1 to r, and we're just looking at the standard, quadratic form or Rayleigh quotient of f with the underlying graph matrix A to analyze the spectral expansion. Thank you. Okay, so I want to define the restriction of our function f, which is on the vertices of x to a link. And I'm going to do this in a very simple way. Given a vertex v and x1, I'm going to define the function f restricted to the link of v, so f sub v, which is going to be a function on the vertices of the link to r. And I'm just going to define this as fv of w is equal to f of w. So it's literally just the restriction of the function to these local vertices. Nothing complicated going on here. And now I can, state the following lemma. That, for any, I guess we're doing the three-dimensional case, but it's true in d dimensions. For any complex x and function f x1 to r, the following two sort of local, local to global versions of this relation hold. So one, maybe the simplest thing, is that the inner product of f with itself is equal to the expectation over a vertex drawn from pi 1, right? Drawn from the marginal vertex distribution on x of the inner product of the local function with itself over the link, right? So this is over pi v1. Right, so the expectation over the local inner products is equal to the global inner product. 2, this is also true when I look at the Rayleigh quotient, when I look at the quadratic form. So FAF, where A is in particular the adjacency matrix of my underlying graph, is equal to expectation over V from pi 1 of FV, AV, FV, pi 1V. So indeed, it turns out that this global quadratic form is exactly the expectation over vertices of the local quadratic form on the links, right? Where this AV is the underlying graph adjacency matrix of the link of V. In the three-dimensional case, the link just is a graph, so this just is the corresponding graph. Okay, I'm not going to have time to both prove this and show how to actually use this to bound lambda. So for now, I'm going to leave this, I think, as an exercise, because what this is exactly this local versus global conditioning that we spent half an hour on in the beginning. Right? What this is essentially going to be. This is an expectation. So I'll give like a 5-second moral answer. This is an expectation over a vertex drawn from pi 1 of f of v squared. Right? That's just the definition of this inner product. This inner product is what? It's the expectation over v. And then this is the expectation over w drawn from the conditional distribution on V of FV of W squared but FV of W is just F of W, right? That's how we defined F. So this is the expectation over the marginal distribution pi1. This is the expectation over V drawn from pi1, and then W drawn conditional on V. But using similar arguments to be used just in the graph case, it's not hard to argue that W is just distributed like pi1. That when I draw W and V like this, right, I draw V and then W conditioned on V, this is the same as drawing an edge in the graph, right? This is what we did in the beginning. And W is just sort of the other random half of this edge, right? So this, you can prove pretty easily, is also just distributed like pi1, which means that, this expectation of FW squared is still just the expectation of F over pi1 squared, which is exactly what this global inner product on the left is. So this is, exactly this local versus global conditioning argument. And the argument here is exactly the same. So I'm going to leave that as an exercise to do. It's just that this inner thing is now an inner product over pairs, over edges, instead of over vertices. And drawing over V, it looks like a random triple instead of a random edge. And so it's sort of a one-dimensional higher version of exactly the same argument. Okay, so I'll leave that as an exercise. And let's actually finish the proof. Do I have like 5 minutes? Yeah. Maybe I'll take 10 or something if that's okay. We can finish I think we can do the proof of trickling down. I'll erase the d-dimensional version. Okay, so now we're almost in good shape, right? Because I have spectral bounds on these local graphs on AV. I have the FAF. I just didn't prove for you, but it's true that, right, this is equal to the expectation over these local graphs on the links. And now, okay, what should I do now that I have these local Rayleigh quotients? Somebody said something quietly, but I couldn't hear, right? Okay, good. We want to use expansion. What does expansion say? Expansion says, on the link, that if I have some function g, if I have g, which is orthogonal to the all ones vector, but if I have g, this just means the expectation of g over the link is 0, then spectral expansion tells me that g, AV of g, is less than or equal to lambda g. So, okay, we want to apply this, but we can't. Why? Because it's true that F has expectation 0. This is true globally, right? Because it's the second eigenvector, which means it's orthogonal to the all ones, right? It's projected away from all ones. But unfortunately, I've localized here. There's no guarantee that these local F of V's should have 0 expectation, right? I know that maybe on average they have 0 expectation, but locally here they don't. So what am I going to do? I'm going to use the most standard trick in the book in expansion. I'm just going to split F into its parallel and perpendicular parts. Then I'm going to handle the parallel part separately. I'm going to claim it's small because globally it's supposed to be small. And we'll see exactly why that's true. And then the perpendicular part, I will just bound by expansion. So it's almost what you said, but we have to subtract out the parallel part. It's only difference. Okay, so let's write F as equal to F parallel plus F perpendicular, where this is just the expectation of FV. This is just the expectation of F over the link of V times the all ones vector, right? So it's just the parallel component. And this is just F minus F parallel, right? So this is the component along eigenvector, all ones eigenvector. This is the component along lambda 2, et cetera. Okay, so I'm not doing anything, clever here. I can break this inner, using the fact that these guys are orthogonal, right? The parallel and perpendicular parts of inner product 0. I can split up this inner product as FV parallel, AV, FV parallel plus expectation FV perp, AV, FV perp. Okay, so far so good. I just split up the parallel and perpendicular parts. I haven't done anything particularly clever. Now, one thing, AVFV is just FV, right? This is the all ones vector. This is the one, value one eigenvector here, so I can just erase AV. And over here, now I do indeed have a perpendicular function, so I can apply expansion now, right? So this will be less than or equal to expectation by 1 of FV parallel plus lambda times expectation. I'm going to stop writing the v in pi 1, but it's always over pi 1 of FV perp AV. Sorry, no AV anymore. FV perp, right? I've just applied expansion, and the fact that that was yeah. So these inner products are always over pi v 1. Thank you. Right. So these are all the local inner products. Okay, there's one more step here, which is that F perp is equal to F minus F parallel. Wait, sorry, let me double check. This is what I want to do. Yeah, this is F minus F parallel. So I can write, maybe I'll just do it here. I can rewrite this as F minus F parallel V, F minus F parallel V. But now I have F parallel V's on this side and F parallel V's on this side, so I can move the lambda factor. I'm subtracting a lambda factor of F parallel V, right? So I can move to FV, and have a 1 minus lambda factor over here. Right? All I did was I wrote the original FV perp as F minus F parallel, and then I grouped together the F parallel terms. I haven't actually done, I just reorganized the terms. I haven't really done anything here, but I did this so that I could get this expectation to look like Garland's lemma, right? Garland's lemma said that the expectation over V of the inner product of the local FV with itself, this is just equal to lambda times the global inner product of F with itself. I guess I hand waved the proof of this, but this is just 1. Right, so this term just becomes plus lambda. Yeah. So I played a little fast and loose here. There are some terms that cancel because of being parallel and orthogonal. Yeah. Okay, so we're left with bounding this term. Right, I said we handled the orthogonal term using expansion. Now we have to analyze this this parallel term. And once we do this, we're going to be done. Okay, so let's look at this inner product. So what is FV parallel? FV parallel. Okay, remember how FV parallel is defined. This is just the expectation over the local neighborhood, right, over the link of V of F times the all ones vector, right? So this inner product this is just equal to the expectation, the local expectation of FV over the link squared, right? Because this is then, I'm just pulling out the constant terms. Then this is multiplied by the inner product of 1 with itself, which is 1. Okay, how am I going to show that this is small in expectation? The trick is to remember that the local expectation of F is exactly how the action of the adjacency matrix is defined, right? So we define the weighted adjacency matrix A, this time AV, to say that, AV, the one skeleton adjacency matrix A, to say that AF of V is the expectation of F around the local neighborhood of V. That's exactly what this is. This is the expectation of F around the local neighborhood of V. So I can rewrite this expectation of this inner product, Right? This is exactly the expectation over pi 1 of AF V squared. Right? This term, I've just traded in how I decomposed F parallel to this term. This is just the inner product of AF with itself. This is the definition. But F is the second eigenvector of A. So this is actually just equal to lambda 2 squared. So altogether, we get that, right, FAF is lambda 2, because F is the second eigenvector. We get this inequality that lambda 2 is less than or equal to 1 minus lambda times lambda 2 squared plus lambda. And I claim that if you solve this quadratic, which I'm not going to do on the board, right, this is a quadratic in lambda 2. We can do 8th grade math. And we'll get that the solutions, the possible solutions, are lambda 2 is less than or equal to lambda over 1 minus lambda, or lambda 2 is greater than or equal to 1. But the one skeleton is connected. So this term can't possibly be the case, right? Because we saw that being connected is exactly your lambda 2 is strictly less than 1. So this can't possibly be the case. And we end up with the bound lambda 2 is at most lambda over 1 minus lambda for the link expansion. Okay, so that's the full proof. Morally, what did we do? We just said that this inner product, this quotient, right, of the inner product of F with AF, we can express it as a local, as an expectation over local inner products of the one skeleton, bound them by expansion, and use this local and global connection to lift it back to a bound on the global expansion. And that's, in a nutshell, the local to global method. It's used all over the place in high-dimensional expanders. We'll see another version of it in the next 2 lectures to bounding the mixing time of random walks. But I think I'm about 5 minutes over, and we proved the theorem, so I'll wrap up for today. Oh, maybe I'll say there are notes posted on the, if you go to the lecture schedule, I guess, there's full notes posted that have more details on all of these things as well, if you want to go through all of the steps more carefully. There's also exercises for the section posted in the appendix at the end of the notes for all the lectures. You can look at those.